In order to be successful in this lesson, it is important that you take a look at the learning goals before starting it and identify which slides will allow you to accomplish the learning goals and success criteria. So take a look at all the learning goals that you see on this slide, go through the presentation, use the student version to fill in blanks as you watch this video, and you can rewind and fast forward as you need, and see which slides allow you to answer or accomplish the learning goals. And then you can even write little notes about each learning goal next to them. We are now in the optics unit, and the optics unit really is the study of light. It's the study of how light interacts with matter, for example. So if light hits a surface, does it bounce off it? Does it go through it? It's a study of how light travels. And so what we're going to do is we are going to start off by taking a look at what light is, and then for the rest of the unit we're going to see how light actually behaves when it interacts with different surfaces, and we'll also get to examine different optical phenomena that you may have already heard of, already seen, but are not quite sure how to explain. So first we're going to start off by defining a wave. And the reason we're starting off with a wave is because light is actually a type of wave. So a wave is just a disturbance that transfers energy from one point to another without transferring matter. Now the best way to understand that is by studying a wave that you're more familiar with, like a wave that you might see in water. And so what you can see here is that you have movement of water from one area to another. Now, as that water is moving from one area to another, we can see there's a duct over here. Now, that duct moves up and down on the wave, but is not moving forward or backwards as the wave passes it, which is our definition of what a wave is. It's a transfer of energy without transfer of matter. So in this picture here, the duct would be like the matter, and the wave of water would be like that transfer of energy. The duct, the matter, is not moving, but the transfer of energy, the wave, is moving. And of course, this is another type of wave, but not the wave we're going to study in optics. So now we're going to study the different parts of a wave. The highest point on a wave, so if we're looking at the wave in this picture over here, the highest point is called the crest. The lowest point on a wave is called the trough. The rest position would be the position of the wave, or in this case, because we're studying water, the position of the water, the wave, when there are no waves. So this dotted line over here, it's really in between the crest and the trough. The wavelength is another very important term you need to know about the properties of waves. It's basically just a distance from one place on a wave to another similar place on that wave. So for example, if we choose the crest over here and move to the next crest over here, just next to that first crest we labeled, measuring the distance from this crest to that crest would be the wavelength. You could also choose to measure from this trough to the trough right over, measure that distance from trough to trough, and that's also the wavelength. The wavelength is represented by a Greek letter called lambda, as you can see over here. And we're going to see how wavelength relates to frequency in the next few slides. One thing I do want you to understand about wavelengths is that they're measured in nanometers. A nanometer is about a billionth of a meter. So it's a really small unit of measurement. So an analogy to help you understand that would be that 1 nanometer is to a tennis ball what a tennis ball is to Earth. So if I was comparing a nanometer, let's say a little red dot over here, to the tennis ball would, relative to that red dot, look like the size of the Earth. That's how small a nanometer is. Another important term to understand when it comes to waves is the term called amplitude. The amplitude is simply the height from the rest position to the trough, or you could say from the rest position to the crest. They're equal in length. The reason I'm defining amplitude is because amplitude is actually related to how much energy is within a wave. A wave contains energy. And typically, the larger the amplitude is, the more energy that there will be in that wave. And then the opposite's also true. The smaller the amplitude is, the less energy there'll be in that wave. So we can use these measurements of waves to see how much energy a wave will contain. And that'll be very important when we are studying light waves. Another very important definition to understand waves completely is something called the frequency. And the frequency is really the rate of repetition of a wave. So how often the wave repeats itself. So, for example, if I was looking at the wave below here, the light wave, if the wave passed the dock 10 times per second, that would be the frequency. That's how often a wave passes the dock. So frequency is measured in a unit called hertz, which basically just means cycles per second, how often it repeats itself per second. And it's represented by a lowercase italicized f. This will be important when you eventually study physics in more detail. You'll represent these different terminology or parts of waves using different letters, especially when you use them to do calculations in physics courses in grade 11 and 12. Now, the important thing that I want you to understand about frequency is that it also relates to the energy in a wave. The more times a wave repeats itself, so in other words, the higher the frequency, the more energy there will be in that wave. And so we're going to see that in more detail in a few slides from now, but the more energy there is, if there's more energy in a wave, if there's a higher frequency for that wave. So now we're going to use some physics language. We're going to use the terminology over here, inversely proportional. I'm going to read the statement first, and I'll explain it to you using the picture below. Frequency is inversely proportional to wavelength. So what does that mean? Inverse basically means opposite. So if frequency is inversely proportional to wavelength, what that actually translates to in plain English is that the higher the frequency, so higher frequency, the smaller the wavelength. Will mean a smaller wavelength because they're inversely proportional to each other. They are opposite in trends. Likewise, you could say the lower the frequency, the higher the wavelength. So if we look at the two pictures here, the wave at the top repeats itself much more often. So this is a higher frequency. And if you measure the wavelength from crest to crest or trough to trough, we're going to see how that compares to the wavelength below. This wave here repeats itself much less frequent. It has a lower frequency. Now let's measure the wavelength and compare it to the wavelength above. You can see this is a much larger wavelength than the wavelength above over here. So the higher frequency has a shorter wavelength, the lower frequency has a longer wavelength. And it just seems to make sense. If you have a longer wave, it takes longer for that wave to go through a certain point per second. There's much more distance for it to travel. And if you have a shorter wave, it can pass through a certain point much more frequently per second, as we see in the picture above here. So I want you to start using the term inversely proportional. Basically meaning as one goes up, the other goes down. They're the inverse of each other. So now we're going to bring light into the picture. We studied the characteristics and properties of a wave. We saw all the different parts of the wave. You should be able to draw a wave. You should be able to explain what a crest is, a trough is, what the amplitude is, what the frequency is, and how those different terms relate to the energy within a wave. And how does that relate? Well, the point is that light actually is a wave. It's a type of wave called an electromagnetic wave, and we're going to see what that is in just a few minutes. But what I want you to also get is that there's two main types of general categories of light that exist. There's invisible light, and there's many types of invisible light, and then there's also visible light. And that's right, you guessed it. This relates to what we can and cannot see. We cannot see with our eyes. Humans cannot see with our eyes invisible light, but we can see visible light, and we're going to learn what those two things are. And again, there's many types of invisible light, and there's many types of visible light. So these different types of light, invisible and visible, they're actually going to vary in those different terms that we saw. They'll vary in terms of their wavelength, in terms of how much energy they have, and in terms of their frequency. So what really separates the different types of light are all those characteristics of waves that we learned. Some have different wavelengths, some have different energy levels, and some have different frequencies. And so because there's many types of electromagnetic waves, or many types of light, we actually created this thing called an electromagnetic spectrum. It shows you the range of different types of light organized according to their wavelength, and as a result of that, their frequency. Now, one really important thing I do want you to understand about light waves is that they do not require a medium to travel in. And so what that essentially means is that when you speak, for example, you create sound waves. For those sound waves to travel from you to somebody in order to hear you, there needs to be a medium. There needs to be some kind of substance for that wave to travel through. Now, the substance that we use here might be, for example, air. If you went into space and you were talking in space, so let's say you did not have a spacesuit on, there was no method to communicate, you were just in space without a spacesuit, you were alive, hypothetically, trying to talk to your friend, the sound would not travel from you to your friend, because in space, there's no medium, there's no air. So the sound wave could not travel. Now, light is different. Light does not require that medium. If you were in space and you want to communicate to your friend, having a flashlight with you would probably be a great tool, because the light would be able to travel from the flashlight to your friend. Since there's no medium in space, sound can't travel, but light can. So the thing about electromagnetic waves is that they do not need a medium in order to travel, unlike something like a sound wave, which does need a medium, like air, or it could even travel in water. Okay. So over here we can see the electromagnetic spectrum. We can see there's a variety of different types of light, and we're going to study those different types of light on the spectrum. Just to see electromagnetic radiation defined in more detail. Like I said, light is a type of electromagnetic radiation. An electromagnetic radiation is basically something that travels in a wave pattern, and it's made from both electric and magnetic fields. You'll learn more about that in grade 11 and 12, but that's basically why the light travels in a wave pattern. And the other important characteristic, like I said, is that light does not need a medium. An electromagnetic radiation does not need a medium, meaning it could travel through empty space where there's no air or anything for it to travel through. And like I said, a medium is a physical substance that energy can be transferred through. So air and water are examples of a medium. And like I said, in space there is no medium, and light is able to travel through that, whereas sound, for example, can't. The other characteristic of electromagnetic radiation is that it travels at the speed of light, which is pretty fast. That's 300 million meters per second. Light travels, electromagnetic radiation travels using a form of traveling called radiation, and that just means energy transfer that does not require a medium. So I've kind of said that quite a few times, which probably means it's going to be an important point for you to remember. And just again to define the electromagnetic spectrum, it's basically the entire range of electromagnetic radiation that exists, and this is our electromagnetic spectrum below. So we're going to study the radio waves, the microwaves, infrared, visible light, ultraviolet rays, the X-rays, and the gamma rays. We're going to see their characteristics, and what I want you to pay particular attention to, especially in the pictures, is the length of these waves and the frequency of these waves. So for example, you can see a radio wave has a very large wavelength, and since it's a large wavelength and it's inversely proportional to frequency, it has a low frequency. But something like a gamma ray has a very small wavelength. Low wavelength means high frequency. It repeats itself much more often. So I want you to pay attention to that and think about what that means in terms of energy. Which one has more energy, a radio wave or a gamma ray? Remember, the higher the frequency, the higher the energy. So that's right, you guessed it. The gamma ray has a lot more energy in it than a radio wave. I also want you to pay attention to the applications as we go through the different types of waves. Now, in case you didn't really understand how fast light travels, I said it was 300 million meters per second. At that speed, you could actually travel around the Earth 8 times in 1 second. So that's pretty fast. And yes, this is a picture of your science teachers dressed up as a Flash for Halloween. See if you can identify your particular teacher. So what I want you guys to be able to do is to list the order of the different types of waves on the electromagnetic spectrum from, let's say, longest to shortest or shortest to longest, whichever order I ask you, and also in terms of the frequency and energy. So over here is a neat memory aid, a mnemonic device, to help you remember the order of the different types of light from longest wavelength to shortest wavelength. So Ronald McDonald invented very ugly Xmas games. R for radio, M for microwaves, I for infrared, V for visible, U for ultraviolet, X for X-rays, G for gamma rays. These R, M, I, U, X, G, these are the invisible forms of light. I'm going to put I for invisible. These are the ones that we cannot see. But they are there. We can measure their energy. This V is visible. And you'll notice below it, I put another little mnemonic to help you remember the different types of visible light. These are all the different colors of light that exist, and you may have seen them before in a rainbow. We have Roy, G, Biv. Red, orange, yellow, green, blue, indigo, violet. And that's the order of the visible light from the longest wavelength to the shortest wavelength. So you can use these memory aids to help you remember the order of light on the electromagnetic spectrum in the order of longest to shortest, but you should also be able to change it in your head and do shortest to longest if you're asked that, and also think about it in terms of energy and frequency. And I apologize if this picture elicits nightmares. So that being said, now that you know wavelengths and what it means, and now that you know which type of light has a long wavelength as opposed to a short wavelength, you should be able to attempt a problem like this. You have 3 waves shown to you, and we know that those waves are going to be visible light, infrared waves, or X-rays. And what you need to do is explain which wave corresponds to which terms. So for example, does diagram see an X-ray? Is it an infrared wave, or is it visible light? So try to use your knowledge of wavelength to sort out which wave belongs to which term. The next few series of slides consist of tables that explain the different types of waves. Those tables will have the wave type in it, the wavelength and frequency of that wave, just described qualitatively, meaning compared to the rest of them, relative to the rest of them, as opposed to just using numbers. I don't really expect you to memorize the numbers. I really want you to know how long or short or how frequent waves are compared to others, rather than memorizing the exact numbers and measurements for this part. You'll also see the energy, how much energy is present in terms of, again, a comparison compared to the other waves, and also the use, and you'll see this in your readings as well. So I do want you to focus on these aspects of the different waves. So for example, if we look at radio waves, that's our first wave in our electromagnetic spectrum. It's the longest of all waves, and because it's the longest, you know it has the lowest frequency, and therefore there's very little energy in it. So all you really have to do is memorize the wavelength, and remember that if you have a very long wavelength, then you have low frequency, and if you have low frequency, well, then you have low energy. So you just memorize one thing and remember the relationship between the other terms, and that allows you to remember all the other aspects of that wave compared to others. And then you're going to see, again, uses. So we use radio waves in MRI. When we do MRIs, we use them in radio signals, TV signals, cell phone signals, satellite communication for your internet. So this invisible light, this radio wave that's a form of invisible light over here, is very, very useful. And you don't even notice how useful it is, but you use it every single day. So I want you to pay particular attention to those practical, real-world uses of these different types of light. Similarly, you can study the microwave radiation, understand how its wavelength and frequency compared to that of the radio wave. It's just the one next to radio waves. It's shorter than radio waves, but it's shorter than radio waves. So that means it has higher frequency than radio waves, and therefore more energy than radio waves. So again, you want to be able to compare it to the different types of waves within that spectrum. And then you can see the uses over here as well. So we use them in microwaves, in radar technology. So when a police officer is trying to measure how fast a car is going to give you a ticket, well, they're going to use the microwaves in order to do that. When we also use it for mapping the Earth, so we can actually take pictures using this form of invisible light, because it's not blocked out by clouds like visible light would be if you're taking it with a regular camera, let's say your iPhone or your Samsung Galaxy or whatever the new phone is these days. And a very interesting piece of information is that sometimes, if you've ever experienced this, static on your television or when you hear static on the radio, that's actually said to be due to background microwaves that are spread out throughout the universe. And again, this is a pretty obvious one, but microwaves are used in actual microwaves that you use to heat up your food. The microwaves will basically cause the water molecules to vibrate really quickly, and when things vibrate fast, well, that means there's lots of movement, lots of kinetic energy. Kinetic energy means movement, and that means higher temperatures, so your food will be warmed up, ready for you to eat. Our next wave is our infrared wave. It's shorter than microwaves, so that means it has a higher frequency and more energy than microwaves. And oftentimes you'll experience infrared waves as heat. So when you're holding a cup of coffee, that heat transfer will be usually transferred as infrared waves. We can use them in technology called thermograms, which is basically images made by capturing the infrared radiating from someone's body or from an object's body. And so you might use those in security images. We can also use it for night vision. Oftentimes restaurants will have something called a heat lamp, where they're going to place the food before it's ready to be served, or while it's waiting to be served, so it doesn't get cold and it keeps it nice and warm. We'll use it in burglar alarms and also in motion sensors. Now we get to visible light. Visible light, like I said, is the part of the spectrum that we can actually detect with our eyes. So far we've studied radio waves, microwaves, infrared, which are all invisible. And now we get to this part called the visible spectrum. And as you can see, the visible spectrum is actually made up of all these different colors over here, Roy G. Biv, with red being the longest wavelength, and with our blue-purple area being the shortest wavelength. So from that you can tell that red has the lowest energy, and this purple area here has the highest energy because it has the lowest wavelength and highest frequency. And another thing I want you to pay attention to is that even though this is the color of light that we see, it's really just a small part on the electromagnetic spectrum, right? Most of the spectrum consists of invisible light, and this small part over here allows us to see, and it actually also allows for life. It allows for life. And the reason it allows for life is because this is the part of the spectrum that allows plants to do photosynthesis. It allows for producers to live and for food to exist and for oxygen to be produced. So just think about that as we're going through the electromagnetic spectrum in terms of how that small piece there drives life on Earth. And this is actually the light that radiates from the sun. There's other forms of light as well, but this is the one that you can see radiating from the sun. The numbers here just indicate the length of visible light, the range of length of visible light. So we have our longest at the red end, and then our shortest at the blue-purple end. Now, as I mentioned, there's other types of light that come out of the sun, and one of the most famous ones that you know is ultraviolet light, or ultraviolet rays, or you might also know it as UV. So these ones are shorter than visible light, and because they're shorter than visible light, they have a higher frequency and therefore higher energy. Now, you actually do need small amounts of UV. The UV helps in vitamin D production to allow you to absorb calcium and to allow you to have nice, strong bones. But if you have large amounts, well, that can lead to things like skin cancer. So going out to tan for too long, as we learned in our biology unit, is not a good idea, because that UV light, since there's such high energy in it, damages the DNA in your cells and is more likely to turn them into those cells that go out of control when it comes to the cell cycle. Now, that being said, we can use that to our advantage. We can actually use UV light to disinfect water. We can put a source of UV light into some water, and that will kill many dangerous microorganisms that might be lurking in that water that could make you sick if you ingested them. So here we have a UV stick that you could actually dip in water just to purify it. Here we have some water bottles that actually have a UV stick built into them, and when you turn on the UV light, it will help to kill some of those dangerous microorganisms by basically destroying their DNA so that they can't make you sick and infect your cells when they enter you upon ingestion. UV light's often used to do some DNA analysis and also used in detective work. So when we're trying to identify fluids at a crime scene, for example, blood or semen, we'll often use the black light, which is another word for UV light, shine it in certain areas, and we'll actually see those fluids that are hard to see with the UV light. Under visible light, they're difficult to see, but under UV light, they're a little bit easier to see, and we'll see some examples of that later on. Next, we get to X-rays. They have a shorter wavelength than ultraviolet light, which means that they have a higher frequency and therefore more energy, and they have very important practical applications as well. They're used in medical imaging. So oftentimes when we want to see if you have a tumor, or if you go to the dental office to take pictures of your teeth for cavities, X-rays are able to penetrate the human body and take nice images of what's within your body, so we can identify if there's a tumor, for example, if you have a cavity as well. And you might have also noticed that X-rays, because they have such high energy, they could probably hurt your cells, and actually they do. So even though we use this X-ray technology to screen or to check for certain diseases and things in your body, we need to make sure we do it appropriately, otherwise you could get hurt by them. So you might have noticed that when you go to the dentist, if you take an X-ray, they'll put this heavy vest on you, and that's a heavy lead vest, and X-rays can't go through lead. So what will happen is when they use the X-rays, it'll minimize where it's going on your body so that it doesn't cause any unnecessary harm. It's used at the airport for security. So when you're going through security at the airport, they'll put you through an X-ray machine. The X-rays will pass through your clothes and through your luggage, but it won't pass through something very, very dense like a gun. So that picture will actually show up on the screen taken by the X-ray. And that's the same reason why we can identify tumors in your body when we do medical imaging. The tumor is much more dense since it's a big clump of cells, and so the X-ray won't pass through it as easy as it does other tissues, and that's what we notice when we take the X-ray. Over here we can see an X-ray of bones. Since they're very dense, it won't pass through the bones, so we see that outline of the bones compared to other parts of your body. And we can also use X-rays for examining the inside of engines to check for damage on cars and in planes, because again, it can pass through many things that visible light and other forms of light cannot pass through. And then finally we get to our gamma ray, which has the shortest wavelength of all, and therefore the highest frequency of all. And since it has the highest frequency, that means it has the highest energy. And so we can use it for many different purposes. It's used to sterilize or clean medical equipment. Basically, it kills anything that's on that medical equipment by damaging its DNA. We can actually use gamma rays in short bursts to kill some cancer cells, and we can use it for mapping. We can use it for taking pictures of the world, because again, that can go through clouds and through the atmosphere, and it won't be obstructed like visible light will when you're trying to take pictures of things. You can take pictures from above the clouds using satellites in order to create maps and locations of the Earth as well. This is what we essentially studied. We studied all the different waves on the electromagnetic spectrum. We went from the shortest, so radio waves, all the way to, from the longest, radio waves, all the way to the shortest, gamma rays. We also studied visible light, which is a portion of the electromagnetic spectrum that we can see. It's a very, very small portion, but that's what allows us to see. That's what also drives photosynthesis on Earth, and which is what allows for life. So that tiny part there on the spectrum allows for life. The other parts that are not visible light, they're invisible. They still have very, very important practical applications, even though we cannot see them. And you should know those applications. So just to reiterate here and to come back to our physics terms, the amount of energy in a wave is inversely proportional to the wavelength. So what is that? What that basically means, again, is that as one goes up, the other comes down. So the higher the wavelength, the less energy. The lower the wavelength, the more energy. So over here we have a very small wavelength, and over here we have a very long or large wavelength. So this one here would have higher energy than this one over here. So as you can see from this picture over here, the higher the wavelength, so for studying something like, let's say, radio waves, microwaves, the higher the wavelength, the lower the energy, because energy increases from right to left in this picture. This is a long wavelength, a large wavelength, but there's low energy, which is what's meant by inversely proportional. As one goes up, as a wavelength goes up, the energy goes down. Over here we have a very small wavelength, but highest energy. So for example, in the gamma ray section of the spectrum, we have higher energy, but smaller wavelength. Again, inversely proportional. As wavelength goes down, energy goes up. Inverse proportion. Once again, we're going to use a different term this time, though. We're going to use the term directly proportional. So the amount of energy in a wave is directly proportional to the frequency. That means they go in the same direction. Two terms go, so rather than one goes up, one comes down. This time, if one goes up, the other also goes up. So as frequency goes up, energy goes up. As frequency goes down, energy goes down. So if we look over here, higher frequency, higher energy. Lower frequency, lower energy. So again, over here we have high frequency, high energy. Low frequency, low energy. Directly proportional, same direction. Low, low, high, high. So we're getting to our conclusion now, and what I want you to get again is that we have been studying the wave model of light. This is the idea that light travels, is a form of energy that travels like a wave, okay, almost like ocean waves, except light does not matter, it's energy. Now, the wave model of light helps to explain why white light is basically light that we can see coming off the sun or from a light bulb in your home, from a lamp, for example. Why white light, when you put it through a piece of glass or a piece of plastic called a prism, why it actually splits into a rainbow. So this here is white light that you would see coming off from a lamp or even from the sun. And when you put it through this piece of plastic over here called a prism, it goes through and comes out the other end looking like a rainbow. You can see all the colors of the visible spectrum, the Roy G. Biv colors that we discussed. And so the reason that is because all those colors of light, they always exist, Roy G. Biv. But the waves are really close together. And when they're really close together, our brain can't tell those different colors apart from each other. Our brain just sees it as white light. Our brain's not fine enough to pick up on the small details, so we just put it together as one color, which is white light. Now, when the white light goes through a prism, you'll notice these lines here represent the waves. The waves bend. So the different colors of light bend away from each other. Red, orange, yellow, green, blue, violet. They all move away from each other. And when they move away from each other, there's more space between them, and now our brain can actually tell them apart. Now our brain can say, oh, wait a minute. It's not just one color. I can see some red in there. I can see some orange, some yellow, some green, some blue, and some violet. And right now you're probably thinking, oh, are there prisms in the sky? Because I've seen a rainbow form before. Well, in a way, you're right. There are prisms in the sky. When it rains, little raindrops in the sky will separate the white light, the colors of the white light, so that your brain can actually tell them apart. So when it rains and you see a rainbow, the little rain droplets are acting like a prism. So again, I don't want you to really memorize the numbers for these colors of light. I don't want you to memorize numbers for frequency or wavelength. But what I do want you to know is just a relative comparison. So which color of light has the highest wavelength and the highest frequency or lowest frequency? Which color of light has the lowest wavelength and the highest frequency or lowest frequency? Which color of light has the most energy in it? And you can do that by remembering the relationships. So if you have a large wavelength, you have a low frequency and therefore low energy. If you have a small wavelength, you have a high frequency and therefore high energy. So red, you'll notice, has the largest wavelength of the visible forms of light. I'm not saying of all light, just visible forms of light, which means that it would have the lowest frequency. This form of writing numbers here is called the scientific notation. We'll learn about it later on. And since red has the lowest frequency, that means it has the lowest energy. Violet has the shortest wavelength in visible light in the visible light spectrum. Not of all the forms of light, but in the visible light spectrum. And since it has the lowest wavelength, it has the highest frequency in that spectrum, and therefore has the highest energy. So violet light has more energy than red light, for example. And like I said, when it rains, the rain droplets act like a prism to separate those different waves of visible light, so your eyes can actually tell them apart, your brain can actually tell them apart, rather than just see it as white light from the sun. This is our summary, so please make sure that you go back through the presentation to see that you can identify all the learning goals that I discussed. Make sure that you do your readings in your textbook, and you'll see that on the homework slide. You need to be able to explain that light is a form of electromagnetic radiation and what that means in terms of traveling through space and not requiring a medium. You should know the orders of the different types of light on the electromagnetic spectrum, as well as their applications. You should know the wavelength, the frequency, the energy levels, not with numbers, but mostly with in relation to other types of waves. And again, focus as well on understanding that that visible light, that very small part of the spectrum that we can see, is what drives life on Earth. This is your homework. Make sure you read pages 463 to 469 and complete questions 1 to 9 on page 469. There's a table on page 466 which goes over the applications of the different types of light, so focus on that table especially because that's where you'll see the practical applications in the real world use. Make sure you review this PowerPoint, which you're already doing if you're listening to this, and do any worksheet provided to you in class. If you're an anime fan, you'll appreciate this. If you're not, you're probably wondering why there's a picture of a weird cartoon boy on your slide. Just ignore it in that case.